Hi, let's continue with the next chapter, chapter 2, with section 2.1, solving polynomial equations and finding zeros of polynomial functions. So as we move on, mainly for chapter 2, it's going to be really factoring heavy. So if factoring is something that's still giving you trouble, make sure to either visit me during office hours or reach out to your SI tutor or check out module 0. It has some videos you can always check out. Moving forward, the word polynomial can be literally interpreted as many names, originally from the Greek word poly and the Latin word nomens. In mathematics, the word polynomial is most often interpreted in many terms, as in many terms, meaning a lot of terms, well, it can be more than two. It refers to algebraic expressions in which each term consists of real number coefficients with variables raised to whole number exponents. Here are a couple examples of polynomials. So here we see a combination of terms. 2x cubed is a term, negative 7x squared is a term, negative 7x is a term, and positive 12 is a term. So this is made up of four terms. The highest power, and therefore the degree of the polynomial, is 3. This is because my highest exponent is 3. The next one, we see we have a term made up of 6x to the fourth power, negative 5x cubed, negative 23x squared, negative 7x, and positive 5. Here we have 5 terms. And the highest exponent is 4, therefore the degree of our polynomial is 4. Here we see we have 3 terms, 2x to the fifth power, negative 7x to the fourth power, and 5x cubed. We have 3 terms, and my highest degree is 5 because my highest exponent is a 5. So that's degree of the polynomial. Now, polynomial means many, but if we have 2, we can say binomial, and that means 2 terms. We can say trinomial, and we have 3 terms. And if we have just 1 term, we can always say monomial, or just 1 term. Solving polynomial equations. This chapter will start with a discussion of factoring and how it can be used to solve polynomial equations that have a degree of at least 3 using the zero product property. So this first example, well, I'm assuming most of them are going to deal with the zero product property. For this first example, we see that we have these numbers in parentheses. We have x plus 1, 2x plus 3, and x minus 4. The zero product property states that if I have expressions being multiplied and set equal to 0, then I can set each one of the factors equal to 0. So we're going to do just that. We're going to set x minus 1 equal to 0. We're going to set 2x plus 3 equal to 0, and x minus 4 equal to 0. Because they're being multiplied, that's the main reason we can do this. All right, let's go ahead and solve for x. I move the 1 over, so plus 1, it's gone. I'm left with x is equal to 1. Let's solve for x. So let's get x by itself. Let's move the 3, minus 3, minus 3. 2x is equal to negative 3, divided by 2, divided by 2. You get x is equal to negative 3 over 2. Next, we add 4, you get x is equal to 4. So we have solved the first example. We're left with x is equal to 1, negative 3 over 2, and 4. Those are the zeros of your polynomial. So your instructions might be something like find the zeros, or you can see something as plain as just solve or solve for your polynomial. Let's go on with the next problem, example 2. Consider 2x to the 5th power minus 7x to the 4th power plus 5x cubed. All right, it's not as easy as the example below because it doesn't have our factors as linear factors. So we have to do the factoring by ourselves. Whenever you're factoring, make sure you first factor out the GCF. That is the greatest common factor. So if all the numbers can be divided by a number, that would be a GCF. If they'll have a variable, you would want to factor out the common variable. So here we see they can all be divided by an x cubed. So we divide an x cubed out. We're left with 2x squared minus 7x plus 5 is equal to 0. All right, we see now that we can factor what's in the parentheses. That's a trinomial. Because our leading number is not 1, we have to put a bit more work. I have to multiply my a and my c. 2 times 5 is 10. And think what numbers add up to be your b, which is negative 7. That's 5 and 2, both negative. When I add them, I get negative 7, but when I multiply them, I get positive 10. All right, so this expands to be 2x squared minus 5x minus 2x plus 5. Notice how if you were to combine the terms that you created, it'll add up to be the one you have above. So what we did is we forced 4 terms. All right, now what we do to continue is we group our first 2 and our last 2. Looking at our first 2, I see I can factor out just an x. So we're left with 2x minus 5. And I want to have the same thing in the parentheses. To make that happen, I can factor out a negative 1. So that I have 2x minus 5. All right, so what we have in blue, that factored to be x minus 1 and 2x minus 5. But what we originally factored, the x cubed, that hasn't gone away. All right, now that I have in parentheses a set of linear factors, meaning my degree is 1, there's an exponent, well, there's an exponent, but it takes the place of an exponent of 1. I can set each one equal to 0. X cubed equals 0, x minus 1 equals 0, and 2x minus 5 equals 0. All right. Well, what number can I raise to the 3rd power to get 0? Only 0 works. Here I add 1 to both sides. We're left with x equals 1. Here I add 5 to both sides. And then I divide by 2. We're left with x equals 5 over 2. So those are our answers. All right. I trust you can do the next problem. Just make sure before you start that you move the 18 over. It needs to be set equal to 0. So that we have x cubed minus 2x squared plus 9x minus 18 is equal to 0. Then you can go ahead and continue. Now here, because we have 4 terms, you can start by grouping the first 2 and the last 2 just like we did above. See if that factoring method works. But the answer is in your notes. Notice that each polynomial equation above was solved by having one side of the equation equal to 0 and finding the numbers for which the resultant polynomial on the other side would then equal 0. Therefore, the solutions are often referred to as zeros of the polynomial. The following chart shows 2 questions that would therefore have the same solution process. When considering x minus 2 squared, one must remember that the exponent of 2 simply means 2 copies of x minus 2. So just to emphasize that thought, x minus 2 squared. Well, what if I had 2 squared? we know that means 2 times 2, right? Or 3 squared. Maybe I should use the same number. That would mean 3 times 3. So when I have x minus 2 squared, like we do here, we know that there, that just means x minus 2 times x minus 2. That's what it means by 2 copies. All right, moving forward. Now, if we set x minus 2 equal to 0 twice, it will be a waste of time by getting a solution of x minus 2 twice. X equals 2 twice. However, we introduce the concept of multiplicities. This describes how many times a particular number is a zero of a given polynomial. So here, like our number we saw here, x minus 2 squared, because it has an exponent of 2, that means it has a multiplicity of 2. So let's do these examples. I'll do 5. Example 5. Find and state the multiplicity of each zero. So nothing's really changed from our prior knowledge. We're just solving the polynomial. So let's go ahead and solve. We see we can factor out a GCF of x squared. So we have x squared. If we factor out x squared, we're left with x squared minus 5x minus 6. All right, here the leading coefficient is 1, so it's a bit easier to work with. What numbers multiplied by negative 6 back to give you negative 5? 3 and 2. Oh no, not those. 6 and 1. 3 and 2 would work, but when I work with the signs, it doesn't match up. I need to have a negative 5 and multiply again negative 6. So negative 6 times 1 gives me negative 6, and negative 6 plus 1 gives me negative 5. That one works out. So this factors to be x minus 6 and x plus 1. And the x squared did not go anywhere. All right, so let's go ahead and find our zeros. Let's set each one equal to 0. I'm left with x squared equals 0, x minus 6 equals 0, and x plus 1 equals 0. All right, so we move 6 to the other side. I'm left with x equals 6. Subtract 1, x equals negative 1. And here's the multiplicities come to play. I have x squared, so it would be a waste of time to take x equal to 0 and x equal to 0, right? That's not what we want to do. What we prefer to do is just take the x and just set that equal to 0. And know that this one is going to be repeated twice. Therefore, since our question is saying to state the multiplicity, I do just have to write a statement as that x equals 0 has a multiplicity of 2 because of that exponent of 2. This x equals 6 has a multiplicity of 1, and x equals negative 1 has a multiplicity of 1. We know multiplicity based if it's raised to an exponent. Whatever that exponent is, that's the multiplicity. Let's go do example 7. All right, so let's go ahead and set each factor equal to 0. This factors, so we have 5 and negative 2. That doesn't factor. So we would have to use quadratic formula. All right, so let's go ahead and start with the first one. I have x squared plus 9 equals 0. We move the 9 over. X squared equals negative 9. We take the square root of both sides. We're left with x equals plus or minus the square root. What is the square root of a negative number? We write I, right? And the square root of 9 is 3, so that would be 3i. Now for this one, I would have to do quadratic formula. So I do negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so I have negative, my b, so I have a, b, c. My b will be negative 2 plus or minus the square root of b squared minus 4 times a times c all over 2a. So that gives us 2 plus or minus the square root of 4 minus 20 all over 2. So 2 plus or minus the square root of negative 16 all over 2. The square root of 16 is 4, but because we have a negative, it will be an I. So I have 2 plus or minus 4i all over 2. All right, so because I have a plus or minus, I have 4 different answers, all with multiplicity of 1. My answers are x is equal to negative 3i, and x is equal to 2 plus 4i over 2, and 2 minus 4i over 2, each with a multiplicity of 1 because they don't repeat. Now, i's are a problem. In our Cartesian plane, if we think of a Cartesian plane and the numbers within a Cartesian plane, there's x's and y's, there's negative numbers, there's positive numbers, and more negative numbers, but nowhere are there i's. I values are complex. And if they are, they just don't get graphed. They don't touch the x-axis. Let's continue reading. Notice that the complex zeros came in conjugate pairs. This is not just a coincidence. With this question, for many polynomial functions with real coefficients, the complex zeros will always come in conjugate pairs. Considering both the square root property and quadratic formula's use of one of the plus or minus sign, it should be easy to see why complex numbers come in pairs. In summary, for any polynomial function with real coefficients that has a 0 of a plus bi, the polynomial will also have a 0 of a minus bi. So just to emphasize, same terms with a plus and again with a minus. That's what it means to be a conjugate. Same terms written once with a plus and once with a minus. Example A, consider a polynomial function with the real coefficients with the zeros at 5i and 3 plus 7i. What other two zeros are in this function? So we have to consider this one to be written as 0 minus 5i. So therefore that would give us a positive 5i. And for the second one, I would just have to change the middle sign. So write as a minus. All right, that's it for this section. Again, this one's really factoring heavy. Make sure you check out Module 0 if it's something that seems a bit a while since you've last practiced it. All right, thank you.